the underpin, give an empirical motivation for that area. Okay. Now, what do we, so of course, if I am to prove that something is quantum, I first have to describe what I mean by classical. Okay, classical is also something you have to define beforehand, right? So that I will define, and then I will clarify that if I define classical gravity in that way, then and if you take quantum matter, okay, which means that matter can be in any kind of superposition, quantum superposition, and you have classical gravity, gravitational field mediating between two such quantum systems, you can never entangle. Okay, so this is essentially a rehash of that local operations and classical communication cannot entangle, which is basic theorem of quantum information. When you start with disentangled states, that you cannot entangle them. Okay? We even extend this to use that to define entanglement in the mixed state case. Okay? Now, then I will go for a schematic of my proposal, okay, based on Newtonian interaction and give some orders of magnitude, okay. And here you will see that to do such a test, one of the best ways is to bring two communities together. So there is this matter wave interferometry community, which has recently progressing towards doing matter wave matter wave kind of optics or matter wave interferometry with nanocrystals, okay, which are significantly larger than atoms and molecules. And then quantum information techniques of spin qubit manipulation. So these can be brought together, and we can use notions from quantum information, such as how you do quantum gates and what is an entanglement weakness to fruitfully. Okay. Now, I will also then say a little bit of why earlier ideas are not fulfilling everything that we want to show the quantum nature of gravity, like why they will stop short. Okay. Then I will go to the experimental challenges. Okay, so that part is really more technical. Okay, and there would be a lot of formulas and stuff, but I will try to explain more the ideas behind them rather than the details of the formulas. Okay, so and what remains to be done. Okay, so there are lots of challenges still left. Okay, and then I will say why this is still a fruitful endeavor. Okay, so that if you go on this route on trying to create large and large superpositions of a mass being here and here, which is what we require for our experiment, then that will already give you benefits in other ways. Okay, and as you can obviously guess, it's a very quantum state, so it's a very good quantum sensor, okay, for inertial forces. Right. So an important question is whether gravity is quantum. Okay, so here I have italicized the whether because that is the question we can answer. We cannot answer the question of the theory of quantum gravity. Okay, we can just answer a bell-like question here, whether gravity is quantum. Okay, now what are the ways one might go about trying to check it? Okay, so one could try to use old quantum mechanics, and in that to do anything that way is very hard. Okay? For example, if you think of 100 Hertz gravitational wave falling, okay, on a detector, first of all, you have to have a detector large enough to be able to, see that wave. Okay. Now, supposedly you do something like that. Okay. Even then, it will just cause a nanokelvin difference in temperature. Okay, a single graviton of the gravitational wave falling on it will cause such a less change. Okay, so that you have to detect that against the background of a huge apparatus such as LIGO. Okay, so it is a difficult, very difficult to detect from energy level quantization alone. Okay? Then the other thing is when you go into say quantum field theory, you have various loops and various things, so you can have corrections to various variables and potentials. Okay? You also know things like lamp shift and stuff, which were examples of quantum corrections for electromagnetism. Okay? So likewise, even the potential that we know is the Newtonian potential will have other corrections which are H bar dependent corrections. Okay. However, the problem is these are also H bar times smaller than the Newtonian interaction. As you will see that we do our best and very hard, and then we try to detect an effect which is triggered by the which controlled by the Newtonian potential. So if you want to see anything, better than that, it is very difficult. Now, and you better not bring things closer than 10 microns of distances, because then the electromagnetism will take over. Yeah, so I'll discuss a little bit of that later on. Okay, even for neutral objects, electromagnetism will take over. Okay, so so essentially we want to use just the Newtonian effect, okay, which is the largest gravitational effect. Okay, and we want to prove the quantum nature of gravity using that. Okay, so what we are going to rely on is this entanglement conveying ability. Okay, that as a non-classical property. So essentially, what we are going to check is for one non-classicality of gravity. Okay? This does not mean. So we does not. I'm loosely calling non-classicality as quantum here. So we are showing that the gravitational field is not classical. In order, if the results of our experiment have to be valid, okay, then the gravitational field cannot be classical. And one non-classical property is the entanglement conveying property. Okay, so a classical entity cannot convey entanglement between two places. Okay? So that is what we are going to rely on. Okay. Now, right. So a little bit of a backdrop, as this will put you at ease with the kind of setting we are operating on. So there's one very popular way of doing quantum gates. Okay. So Harosh did it earliest in 1997, but more recently with superconducting qubits. And there's a microwave bus, a strip-line superconducting bus between them. People do gates through these kind of methods. So what they do is they exchange a virtual photon through this microwave bus. Okay, so the qubits, qubit 1 and qubit 2 are detuned. Okay, from this strip-line resonator. Okay, and they do not really deposit an actual photon here, but these are virtual photons which propagate through them and cause an interaction. Okay, by virtual photons, what do we mean? Virtual photons are photons which are, virtual excitations of the electromagnetic field. So they do not obey the equations of motion. Okay, so they are not a photon traveling along the mass shell; they are off the mass shell. Okay. So those are the kinds of entities which are exchanged, and then you have a coherent interaction between qubit 1 and qubit 2. Okay? Those coming from the atomic physics side of quantum optics might be familiar with things like transitions in a lambda level system. So there is an analogy here with that. Okay, it's a bit like you're going between the two levels are like going halfway between, going to superposition of the two levels is like generating the entanglement. Okay, this similar situation with the two system case, and this intermediate level is never occupied if you detune your pulses very much, the pulses which cause the transition to the intermediary and back. Okay, so it's a complete analogy with that. Okay, so that is a case when the intermediary in practice is eliminated and you have a coherent interaction between the two entities. But that does not mean the intermediary is not there. That's the most important point. Okay, the intermediary has to be there. Okay, and is the intermediary which causes the interaction. Okay, so when you find what you find through this is a coherent gate between qubit 1 and qubit 2. Okay, something like an interaction sigma dot sigma will happen. Actually, flip flop, like sigma plus sigma minus plus sigma minus sigma plus will happen when you have only virtual photons being exchanged. Okay, now you may also actually think of taking away this bus. Okay, just move it from the middle. Okay, does not matter, because essentially that is how all interactions happen. Okay, Okay, so there are, Coulomb interactions, dipole-dipole interactions between objects, and they actually happen all the time due to these virtual photons in the middle. Okay, we just don't see them. When you put a cavity, you kind of direct them to have more weightage between these two qubits than all over space. Okay, but nonetheless, that phenomena is always there. The intermediary is always there. Okay?
Can I ask a question here?
Yeah, sure.
Yeah, so you're basically saying the electromagnetic vacuum can be a mediator of entanglement. So let's say electromagnetic vacuum is omnipresent, and you take any entity you like which lives in this electromagnetic vacuum, then in principle, if I could integrate out the vacuum, you will tell me in essence all bodies which were there in this background has developed entanglement. Is that the statement? And
yeah, pretty much. So the thing is, of course, those entities must be interacting with the electromagnetic vacuum, right?
Right. Sure.
So it has to be a charged entity, and you have to create a situation for. So normally, when say you just place a charge here, just place a charge here, of course they are interacting, but that interaction is then the stable state of the system, right? So to see some entanglement, you need to part of that, change that. Okay.
I see.
And in general, so if you remove this bus and kind of try to extract just from the vacuum, it'll be very, very inefficient, right? So that's why when you connect qubits, you use a bus, right? So
maybe I kind of connect it to one more example. When you look at Casimir effect, we think it's coming from vacuum. Can I say that when I put the plates together, there's a vacuum force acting on them, but it also means the two plates are entangled. And now if I very adiabatically take it very far away, do you think the entanglement remains for the Casimir force? And the force has gone to zero, but the fact that they were at some point feeling this force will convert itself into a presence of entanglement. Can one say this? Is it possible?
That's a good question. So we have also calculated in a recent paper with actually two people in the audience. So I haven't put it here particularly, but exactly in the same way as I'll be speaking about gravity, the Casimir force can also entangle. Okay. Now, what you're asking is that after you have entangled, if you are taking them slowly far away, so the entanglement will remain as long as all the relevant decoherence and the fact that it will thermalize also. So it's the entanglement. Then you're looking at a non-equilibrium situation in some sense.
That is true. Yes.
The equilibrium entanglement will obviously gradually go to zero because the force is decreasing. But if you can do it in a well-protected manner, you can probably take these entangled states to a more distance and exploit it for something. I mean, if you do the process, say teleportation, if you manage to do it before,
Okay. Thank you.
So I have not brought that, but I can send you that paper. So Dipankar and Urvasi are also collaborators in that one, but I did not put that up here actually. Yeah, but I can send that.
Thanks.
Now, actually, quantum, so essentially, this is again re-emphasizing the previous point that even historically the Newtonian interaction was discovered, of course, by Newton, okay? So 1600s. And we have been using this ever since, and something which you have been using from much before quantum mechanics and measuring, you can get the false sense that must be a classical interaction. Okay? But what I'm showing here is that in this slide is that there's a perfectly quantum mechanical way through the exchange of this off-shell, graviton, which I have put it there as quantum communication to emerge the Newtonian interaction. Okay. And then the question is that, and it is all valid for completely varied with both quantum mechanics and relativity put together. So this is in full quantum field theory. You can emerge this 1/r interaction. So then the question arises is that what is the true mechanism? Okay, so is it that quantum field theory mechanism, okay, which is this one, where you have a quantum entity being exchanged, okay? The quantum entity, of course, are in this description are these virtual gravitons. Okay, they are not on-shell real gravitons, so they are not like the photons of an electromagnetic wave or the gravitons of a gravitational wave, but they are gravitons which are sourced by these masses and absorbed by this sink mass kind of within the background vacuum field. Okay, so that can give this interaction potential. Okay, and it is the same in all branches of quantum field theory. So we know that Coulomb force can be explained that way. We also know that the forces between the weak interaction force between two weakly interacting particles actually was formulated originally in that way, and it can be explained like a Yukawa interaction. Okay, and then also those between quarks can be explained like almost a delta function, but with spin-dependent terms and stuff like that. Okay, so those are like the Newtonian things. Okay, and we want to find out the hidden intermediary is quantum or classical. Okay, so if it was a classical entity, these are depicted here in a cartoon way. A classical entity does not change if you measure it. Right, so this is the detector. Then the masses interacting through such a classical gravitational interaction cannot entangle. Okay, I will explain this slightly better. Okay, right. So there is a question: can a method be developed experimentally to observe the virtual graviton? This is exactly what I'm trying to go towards. Okay, we claim that this is what we are doing. Okay, to the full extent what we are doing, that is a bit, so we can discuss that. Okay? Definitely we are discussing the quantum nature of gravity here. And on top of that, if you put the fact that, so was this the next slide really? Yeah. Okay, I'll come back to that question on the chat maybe slightly later. Okay. Now, so let us make one assumption and one definition. Okay? So we work under this setting. Okay? What is the assumption? The assumption is that interactions are local in nature. Okay, so whenever you have a source of gravitational something which sources gravity, the stress energy tensor. Okay, so T00 is just the mass. Okay. It couples with a weak, a small perturbation on the Minkowski background. Okay, on flat space background, you can imagine gravity when it is weak. Okay, just like a quantum field theory. You do not have to think of it as a curvature of space-time in general. When it's quite weak, you can think of it as on the flat space you have at every point a field, a tensor field h mu nu r t. Okay? And that, just like any quantum field, and that couples to sources, okay, in this way, okay. And this k square is the gravitational constant g, okay. So that's the strength of that coupling, okay. Now, why is this locality of interactions coming? This assumption of locality of interactions is essentially the same assumption as relativity, okay. Relativistic causality means interactions must be local. Okay, if instead of r here you had r plus some other distance, then you're having a non-local interaction, right? So interactions are local. That is very much a result of relativistic causality, and this we assume. We do not prove that. Okay, within our experiment, we cannot prove this because it's very difficult to make things move fast enough. So what we are working with in a setting is that we are assuming relativistic causality. Okay? And I think this is a safe enough assumption if you believe in relativity. Here we are trying to prove the quantum nature of gravity, so we do not have to prove the relativistic nature of gravity as well in the same experiment. Yeah, this is my claim. So that we assume. Once we assume relativity, which means that the interaction of a mass with its local gravitational field is at that point. It's a local interaction. So essentially, this gives locality of the interaction, and it means this necessitates a mediator. So this, when you are speaking of interaction between two masses, it necessitates a mediator to having to go between them. Okay, so what I'm telling is the mediator is coming purely from relativity. If you did not have a mediator, you have to have an action at a distance, right? So that is the problem essentially. Yeah? So we are justifying the mediator from relativity. Okay? Now, moreover, we have to also define what we mean by a classical field. Okay, so what do we mean by a classical field? Here we mean something which you can have quantum states of objects if you want. That is completely fine. Okay, matter, which will be our nanocrystals, can be in whatever quantum states you like. Okay, but the gravity they source still has to be classical. Okay, so here I have drawn it as a curvature, but this could also be as a tensor field in a flat background. Okay, it has to be numbers at every point in space-time. Okay, a collection of numbers if it's tensor. Okay, it can be related to whatever quantum state matter is, but the field should be classical. Okay, so that is a definition of classical field. Okay, on top of that, it's fine to have fluctuations. Okay, so as you know, quantum mechanics is not about fluctuations alone. Okay, quantum mechanics is about fluctuations in two complementary bases. Okay, so if you find a lot of correlations and random fluctuations in single basis, it's not quantum. Okay, it's a classical statistical theory. So this is what I'm telling here. You can have a classical statistical theory where for different matter states, you randomly have different gravitational fields, say in space-time, with random probabilities. But that does not mean anything about the thing being quantum. Okay, for quantum, you require at least to know that the gravitational field kind of has fluctuations in more than one basis. Okay, we'll not directly do that. We will do that indirectly through the entanglement. Okay, but anyway, this is our definition of classical field. Okay, so whatever is quantum matter, its sources just numbers at a distant place. Okay?
So one more question here. So the T mu has matter into it. I mean, these are the matter momentum, or just the field momentum? I mean, it also includes matter.
It includes everything that sources gravity.
Okay, I see. Okay.
So, in general, in our case, it will be specific case. It will be just a nanocrystal moving very slowly, so it will just be its mass. Okay?
I see.
But in general, it's all the fields, including the gravitational field itself. Okay,
yeah,
but that is difficult. There's a higher order effect then. Okay?
And the h mu nu is essentially the metric being expanded, the first term being the g mu nu, which is the flat metric, plus this one, is it? Is the first term.
Exactly. So I somehow lost that slide. I should have put a slide there. So actually for the, maybe I try to see whether I can write here. Yeah, annotate, yeah. So draw. Okay. So sorry that I forgot to put that. It was usually is there in my slides, but so G mu nu, the general metric, is expanded in terms of the Minkowski metric eta mu nu plus this H mu nu. Okay, so it's a weak, it's a weak perturbation on the flat background, and pretty much since our fields will always be weak in the regime we will be working, we can always consider gravity as a field in a flat space-time background. Okay? In fact, you can consider that to all orders as well. Okay, I don't see any fundamental problem of that. Thinking of it as curvature is just another way of thinking about it. Okay. Now, let me clear. Why can't I go to the next page now? Because I'm still annotating. Yeah. So now I'm just going to go something which will be very familiar to people who have been exposed to quantum information, okay, on particularly to things like entanglement distribution and entanglement distillation, is this basic notion that local operations and classical communication between two objects cannot entangle them. Okay. So as I emphasized in the last slide, where am I getting my local operations with? Why does one qubit only interact locally with other things? It's just because of the locality of quantum field theory, the locality because of relativity. Okay, more basic than. So sorry, not quantum field theory, because quantum is what we are wanting to prove. Just from relativistic causality, interactions must be local. So whatever interacts with qubit A over here, qubit held by Bob, must be something local. Okay, so that's why we have only local operations. Okay? Now, with that local operation, if you add only classical communication, so only classical entities can go, so classical fields can go. So like I'm communicating with you through classical field, through electromagnetism. Okay? Thanks to Jagadish Chandra Bose long time ago that I'm able to give this, this Zoom seminar. Okay, but or of course Maxwell and Hertz as well. So the thing is that when we communicate classically, I'm not able to generate an entanglement with you, right? I really need to send you photons to entangle, right? So essentially, that is the basic idea here. Okay, and then just a simplified explanation of it. When your local operations are just, you have some classical field generated here, and that couples to the quantum operators here. All you have at best are local unitaries. So it's trivial to see that if you start with the product state, you remain a product state. Okay, so you do not generate entanglement. And these people have also, you can write it slightly more generally. You can start with what we call arbitrary separable states, okay, with probability distributions over various, pairs or various correlated states, okay, classically correlated states, okay. So and then you can also generalize the operations. They need not be local unitary operations. Of course, the field you may interact with the field, but the field could interact with other qubits, and your system may interact with other systems. So essentially, what you have is, completely positive trace preserving maps. If you have that, even then it is very easy to show that you do not entangle. If you start with separable, you do not entangle. And as I have emphasized in the previous work, so our previous slide, that this is our, we are taking that the field to be classical, okay, here. So then that's classical communication, okay, in this way, okay, and then it is clear that this cannot generate entanglement, okay. So this is all the justification I will give. Now I will proceed to the experiment, okay. So Chiranjeev, a little bit about time. How much time have I spent?
You started, okay, so you have spent about 30 minutes.
Okay. So I spent a lot of time justifying my cause here, because usually this is from which I get maximum questions often in the end. So I spend this extra time. Okay. Now I'll go to the scheme. Okay. So what I've justified till now, that if you had quantum matter, okay, so everything is quantized, like these masses and stuff, but the gravitational field they generate is classical, then you cannot entangle. Okay? And the only additional assumption there was a relativity, that you needed something to go from one mass to another, so that you did have a mediator. Okay? And when this mediator is classical, you cannot entangle. Now, how do we actually do it in practice in an experiment? Okay, this comes from the field in which I was working on for quite a while, is how to generate large superpositions. Okay, and that started right a long time ago, actually, when I was working with Dipankar Home back in India in 96, 97. So we were already looking at schemes how to generate superpositions of an object being in one place or another place. Okay? And that time it was through neutrons hitting a plate, a mirror. Okay, so what is a general thing I've realized over the years, that it is far easier to do these kinds of things when you have an ancillary bona fide quantum system. Okay, and you prepare superpositions of that and then use that to prepare other large superpositions. Okay? So that is the scheme I will use. Okay, but before proceeding to that, let me just show that, just do a schematic, that suppose you have prepared a superposition of a mass being here or here. So it is the dotted or the undotted place, and so here dotted and undotted superposition separated by distance delta x, and the centers of these superpositions are separated by a distance d. Okay, so these are in interferometers. So the centers of the interferometers are separated by small d. Okay, and suppose you have held things in this kind of superposition for a while. Now what will happen? Okay. So what will happen is that they will evolve according to their gravitational interaction. And so initially we have prepared left plus right for both of those things, okay? And we let this interaction develop different phases, okay? Obviously there are different distances. So the RL has a much smaller distance, d minus delta x, compared to LL and RR and LR, okay? So all these other phases are much smaller. This is the dominating phase, okay? This phase evolution is happening purely due to the Newtonian interaction and E equal to h nu kind of principle, okay? So the energy, yeah, and by h bar is the frequency of evolution, okay? So that's how the phases will evolve. Okay? Now, what happens is if we write this, okay, we can take the common phase out. So the phase RR and the phase LL will be the same. So you can take something out, okay? And then you will see in the middle with L, what if you take L common, what you have, and if you take R common, what you have, they are not the same, okay? Generally, delta phi LR and delta phi RL will not be the same because of different distances. And if they're not the same, then this is an entangled state. So what happens due to the gravitational interaction is that these two masses entangle. Okay? So those who are familiar with, say, quantum computing or with, condensed matter physics, maybe a different language is better to use. So these L and R are a bit like two states of an, Ising spin, okay? So left and R are like two states of a qubit. And you can think that when they are closest, they have a stronger interaction, and when they are separate, they have a different interaction. This is like an Ising interaction, yeah? Pretty much like a 1 plus an Ising interaction. So you have only one of the components strongly interacting. And we know that kind of thing does what is called a CZ gate, control Z gate, or a control phase gate in quantum information. And this is essentially what is happening here. Okay? It's a control phase gate which entangles those qubits. This control phase gate is mediated by gravity, unlike in quantum information is usually mediated by electromagnetism, right? Of course, because that's a much stronger interaction. Now, we consider a special limit to understand the full, nature of full strength of the effect. Okay, because often people have this, erroneous perception in their mind that gravity is always weak and you will never do anything, reasonable with it. So we try to make a best possible estimate here. So essentially, we think of a case where you have managed to make superposition sizes of mass being here and there much larger than their closest approach. Okay, so this closest approach is much smaller than all these distances. So then only one phase term dominates, and this is the only one we have to estimate to see the scale of the effect. Okay. But there is one important thing first, okay, is that when you bring things too close, okay, they will also start interacting electromagnetically, okay, even if they are completely neutral. Okay, so no charges, neither any multiples inside those nano objects. So they are often random charge multiples. And suppose we have got rid of all of those. So these are really pristine neutral masses. Even then, when you bring them close enough, they will start to interact through the Casimir interaction. Okay? So essentially, there will be instantaneous, from vacuum fluctuation, dipoles will be induced in both those masses, and then they will interact by exchange of virtual photons. Okay? So if you take purely the ratio, so we want the strength of gravity to be more, okay? But when you take a ratio, you see that it doesn't depend so much really on the mass of the object per se. It depends on things like this MP is the Planck mass, and this rho is the density of the density of the object. There's not too much you can play with these things, okay? So these are that is a constant of nature, and the rho is pretty much, for generic substances that you may use, you do not have too much that you can play with rho. Okay, so of course it means that you should try to use solid objects, right, rather than liquids or gases, okay? But other than that, there's not too much you can play with. So essentially, distance is your only handle. And what this tells is that if you just want gravity to dominate over Casimir, at least by a factor of 10, yeah, because we want the entanglement to be due to gravity, not due to electromagnetic interaction like Casimir, you at least have to go to 100 microns of separation, okay, which is quite a large separation, right? Unfortunately, okay, and it places the demands that our superposition sizes should at least be comparable to that, okay? We are not going to demand this tremendous thing of having superposition larger than the lens.
Can I ask a question here?
Sure.
Sorry. Yeah, so here probably the fact that the object is a finite size object has a very important role to play, because when you're calculating the gravity, it looks like you're treating them as point mass. But when you're looking at the Casimir force, the area really matters. Yeah. And then I think the question would be, can I make them into black holes? Let's say extreme limit, you just condense them into points. And then this calculation is ideal in some sense. So I'm just curious that what is the finite size doing here?
Right. So a little bit. So the R's have kind of cancelled because of I use density. You see.
Yes, I see that. So I thought that it's missing, but it's somewhere there, right?
Yeah. It is. Yeah. It is in the density. It got cancelled. So what I am doing here is assuming a standard density of objects. Yeah. Of course, this, if you go to, even before black holes, I think if you go to neutron star densities and stuff, the rho would be much stronger, and it's possible that gravity will dominate before. So, but what I was telling is that there's not too much flexibility after going to solids, in the lab. So this is why my estimate is based on. I mean, there's still something. I mean, people can use things like, later in the atomic series, like, after uranium, whatever is there, but still not too much. So we use standard lab things such as silicon and, stuff like that.
So does the optimization, in a sense, if you make it into parallel plate shape, matters a lot, or it doesn't matter?
Well, we haven't played too much with that. That is an interesting question. Okay. Yeah, but parallel may not help really. Unfortunately, parallel may make it worse. Okay. But what we have is seen that screening gives you some advantage. So this I'll discuss.
I see. Okay. Thank you.
So now an order of magnitude of the effect, okay, is that, so we just put different things here. We put masses of microspheres, okay. So this slide is how the idea struck me, okay, essentially, is because I had colleagues who were trapping microspheres and cooling them into the ground state. Microsphere means micron size radius. This has 10 to the power minus 14 kg. And they are ambitious to want to test quantum properties in the center of mass motion of such objects. Okay? So then the point is, if you take such a mass, okay, and if you prepare a superposition of about 100 microns, okay, and hold it for 1 second, which is a tremendous achievement to be able to do, okay, then you can see that this phase factor turns out to be unity. Okay. And people are still surprised by this, that why it is. So it's like a Hertz effect. So gravity manages to entangle in 1 second, okay? But if you can prepare such 100 microns superpositions, okay, of these microspheres. So there's one way to understand that here, of course, it is E by h bar, yeah, Planck's law. So h bar sitting in the denominator amplifies the effect because it's a quantum phase. Okay. While another way of thinking about it also is that the masses are kind of approaching the Planck mass, They are still much less than Planck mass, 10 to the power minus 14 kg, but the how much distance the light can go in that time over more than makes up for that. So this is another way to understand that phase. Now, let me just go to a little bit of history. So, though we did not arrive at our result from reading this, but historically, very similar ideas were first brought up by Feynman. There was a conference in Chapel Hill in 1957, and when people, so Feynman was questioned whether gravity is quantum, okay, and then as a response to that, he said that let us do an experiment where we create one mass in a superposition using, if it has a spin, then you use something like a Stern-Gerlach to prepare it in two different places. Interestingly, we will be using the same method. Okay. And then you have another mass, and that will then move according to one place or another. Okay, and then so what the exact words he used is, then you have to use quantum mechanics and believe in gravity in order to describe this experiment. Okay, that's as much as he said. Okay, so what does he mean there? So we can of course think a bit more what he meant, but in order to describe this experiment, probably to describe it completely, what you have to do is the two particle correlations here, right? The reduced density matrix of one particle correlation will not suffice to explain all the magic effects in the experiment. So if you did a two particle experiment, then you would need gravity to be quantized to explain that. That was his point. Okay, so we are making that point from a more modern perspective, but also we are making two important observations. Okay, so first of all, the second mass will take a very long time to move, according to what the way Feynman was saying, because the acceleration is 10 to the power minus 16 meter per second square. Okay, so this is not really a good way to entangle. Okay, but this phase development, in 1 second that you have this phase, is a much better way to entangle. So this is one definitely achievement that we are doing here. And also, what aspect of the experiment? Of course, this is there also in his words to describe this experiment, but what really is needed is to measure the entanglement, okay, from some kind of correlations. Otherwise, you do not find about the quantum nature of gravity. Okay, this is maybe another way to say that why some of the things end up earlier. Okay, other suggestions are not fully convincing to explain the quantum nature of gravity. First of all, often people say that, okay, let's prepare a superposition of mass in two places, and then from our classical experience that a mass seeds gravitational field here and the mass seeds gravitational field there, we assume that the same thing is superposed, and then if you bring back and you have coherence, okay, at the end of your interferometry, that would mean that the gravitational fields were in a coherent superposition, and voila. Okay, so that proves the quantum nature of gravity. Okay? But the problem with that kind of thing is that there is no probe to say that gravity was at all, involved. Okay? So we have to extrapolate our assumption that gravity is involved when the masses are not superposed, okay, or measured. And then we have to extend that. Yeah. So this is not, and if you have to find out gravity, you always have to involve another mass, right, as a probe mass. So this already brings us the necessity of, two mass experiments. Okay. Now, within two mass experiments, another thing that was suggested that you prepare a mass in a superposition and you take another mass and it either deflects one way or another. Okay. And some people say that is proving the quantum nature of gravity. But I disagree, because this is a one basis thing. It is like measuring in a Z basis, okay, whether the mass is here or there. And then accordingly, if it was there, this mass goes that way. And if it was here, this mass goes the other way. Okay, so that is not quantum mechanics. Okay, quantum mechanics requires, so this is probabilistic statistical theory that you can test in this way, that if the mass is left, gravitational field is randomly seeded to the left. If the mass is right, gravitational field is randomly seeded to the right, but that is not quantum. Okay, so to really know that the gravitational fields in these two configurations were also in superposition, you have to have another mass coming in, but measuring some aspect of it which involves all the bases. Okay, so this kind of brings us to this entanglement test. Okay, so that's why I think nothing lesser would suffice. Now, coming to the main challenge is how we create this so I will just 1 second, I check who has come here. Elena, don't need. Okay, so then what will happen is that right. So how will we create these kind of superpositions? Okay, these are large mass, yeah, long distance, yeah. So large splitting. Okay, so there are three things. So you have a large mass, you create a large separation, and you hold on for a long time. Okay, I will just be back very quickly. 1 second. Yeah, give me just 1 second. Okay, so then how will we do that? How will we detect, create such entanglement and detect? Okay, so first of all, the usual trick does not work. Okay, so usually how do we create superpositions? We have a large thing such as a macromolecule, and we put it on a beam splitter. A beam splitter can be like an optical beam splitter for macromolecules, or it can be a solid state grating kind of beam splitter. But essentially, what is a beam splitter? A beam splitter is a tunnel thing. So you come from one side and you half reflect and half transmit. Okay, that's what's a beam splitter. Okay, so if you have to do interferometry, you have to have a beam splitter. And the big problem in case of large masses is that if you have a significant distance as we need, okay, and you have a large enough mass, then with large enough barrier, the barrier V size is related to how low in energy you can cool the other mass. Okay, so it needs to be significantly higher than the incoming mass's energy. Okay, so this amplitude is exceptionally small. Okay, this we know is good for atoms moving over distances in optical lattices such as microns. Okay, but this is 10 to the power 13 atoms. Okay, so you just have an incredibly small amplitude, okay? Because this is fully a nanocrystal, a microcrystal. Okay? So how will you do? So we have to use this Tern-Gerlach technique. Okay? So what is the idea? So you have a mass with a spin embedded in it, and at time t equal to 0, you come with a microwave pulse and prepare a superposition of up plus down. Okay. Now you have a large magnet giving an inhomogeneous magnetic field gradient, and the whole mass will move, left or right. Okay, and at a certain time, a quarter of the time of the later, you flip the spins. Okay, so then what will happen? The masses will start to decelerate. Okay, they will turn back. They will reach their highest distances, turn back, and try to accelerate the other way. Okay, then at these times, you flip again so that you start braking, decelerating, and then together they will come back to a point where both their momentum and their positions will coincide. Okay, the center of the wave packets. Okay, so the wave packets are brought into full overlap. Okay, so there is another question in the chat. Okay, sorry. Now, sorry. So now how will we need a little bit more here. We not only need to do this splitting, okay, we also need to hold the masses parallel to each other for a while for a good gravitational phase to accumulate. So what we are thinking of doing at this stage is a sample will not only have electronic spin, which is the one which will have a large Bohr magneton and split significantly in an external field gradient, but then there are also nuclei. So again, in quantum information for memories, you map electronic spins to nuclear spins. Okay, so what we will do is we will map these electronic spins to nuclear spins. Okay, and then they will fall. Then essentially they don't see the magnetic field anymore. Okay, because the nuclear magneton is so small. So they will essentially fall parallel to each other, and there will be a phase accumulation. Okay? And then you bring back, again, map back to electrons, and then you do your flipping at appropriate times and bring back the apparatus. Now, so we repeat now all the calculation that I showed previously with this combination. Okay, so L and R of previous is now replaced by L upspin and R downspin. I hope you understand, because upspin went left and downspin went right in our interferometer. So upspin is always correlated with left and downspin always with right. Okay, and you then go through the whole pulse sequence of that, what I did, just replacing these, and later on bringing both of them to the center. Yeah, at the end of the process, they're brought back to the center. So the masses actually disentangle, the center of mass disentangles. But what happens is the entanglement between the center of masses that was generated due to the gravity is now fully mapped onto the spin. Okay, so this is beautiful. So measuring entanglement between two spins is a highly developed technology in quantum information. In fact, that is kind of the basic zeroth order thing you have to do before you go to grand scale quantum computation. You at least have to be able to entangle and verify two spins. So now we can just measure the spins embedded in the masses through what is called the entanglement witness. Okay, so you measure these correlations, and if this correlation is negative, so essentially this is what happens. You complete the interferometers, okay, and then measure spin correlation functions, okay. If the spin correlation functions are negative, okay, not spin correlation, so this combination of spin correlation functions, yeah, that combination, if it is negative, then that means the states are entangled. Okay? This is called an entanglement witness. Now, you can alleviate our situation a little bit by putting a screening plate, because this is also an advantage of gravity over electromagnetism, that you can actually screen the interaction while gravity does not get screened. So then the Casimir goes away, but there's new Casimir effect of the mass with the intervening plate, okay, which results in some acceleration when they're very close, okay, significant one. So we cannot do this, bring them arbitrarily close, because we have to still use magnetic field gradient to bring it back, you see. But at least it alleviates our situation. We can go to 10 micron separations, okay. And also we try to go to less fields in that way, okay. So now, so less of a phase, okay. So if you are willing to sacrifice the phase and using the screening, then we can go also to a little bit less mass, minus 15 kg, and less distance separation, okay. Which means superposition size can also be smaller, like 10 microns, okay. Now, what are the main challenges in doing this, okay? So one challenge is creating this splitting, for which I showed this Stern-Gerlach method. But nowadays, we have come to learn that there are some barriers to that, okay? I'm not going into that, so that is not completely finished, okay? If anyone is interested, I can comment more on that. However, supposedly, if you had created that, then what are the main noise sources? Okay, so of course your experiment will not happen in complete vacuum, right? So there will be some gas with some pressure, okay? And the thermal de Broglie wavelength of the atoms, even at quite a low temperature, is short enough that if they collide with one component of the superposition, they immediately reveal which path information. Okay? So we do not want any which path information to be revealed, which is why we have to reduce the pressure, okay, the atom scattering. But also the objects themselves emit black body radiation. So from hello, yeah, from Rayleigh scattering formula, we can calculate that you have to cool the object internally very much, okay, because it goes 6 power, which is a challenge. Okay. Some other challenges are external gravitational disturbances, okay, random accelerations. Okay, so they induce significant phase change. Okay, so we have some ideas to handle that. Okay, this is not a very easy idea, but very easy idea conceptually, experimentally, but not very easy idea conceptually, you know. Not very easy idea conceptually in the level of implementation. Okay, so we have to just let the whole experiment with the two apparatus and their measuring apparatus, okay, whichever microwave pulses to be given, and then lasers to record the position, everything in a freely falling capsule. Okay, that automatically gets rid of the external accelerations from Einstein's equivalence principle, right? So all acceleration vanishes, okay? However, what remains is still the curvature effect, okay? Because these external masses will give a 1 by r, and there will be some difference in the gravitational acceleration between two places that manifests as like a potential, like x squared. Okay? And then there's also jitter from molecules hitting from outside the box. Okay, so we have learned, we have investigated how to, you know, alleviate all those things. Essentially, we have calculated pressures which allow you to do this thing. Okay, the type of experiment. Okay, 10⁻³ pascals and stuff would do the outside pressure. Inside, of course, we need still this extraordinary 10⁻16 pascals, which have been achieved in best possible, you know, penning trap experiments. And similarly, you have to keep sources of gravity a bit far. So this gives the very different distances, like for planes, automobiles. As you can see, humans can come like 5 meters, yeah, close. And that was very easy to do because there's a lot of data from the gravitational wave community on acceleration noise near an object. So we can easily convert that to curvature noise, okay? And one can, you know, by multiplying by this factor and evaluate these things, okay? So it can be done, but comes with a freely. These are also very good as sensors, but maybe I don't go into this because of, Chiranjeev, what is the time scale? I've probably gone over an hour already.
Almost over. Like 1 minute, 2 minutes are remaining. Okay.
Okay. So maybe I just highlight the point that if you went to slightly smaller masses now, with same mechanisms, you could still very hard, but presumably you could prepare, if you could prepare such a thing, a meter scale superposition of a 10⁻17 kg mass.
Shogata, you can take 5 more minutes. Okay.
Okay.
I think it is fine. Yeah.
Yeah, but it is kind of my last slide. Okay, so it is not entirely wishful thinking. I'm not just stating that I can do this, okay, or anyone can do this in nature. So we have calculated the pressures and temperatures you need. These are pretty much similar to the experiment on quantum nature of gravity to entangle two masses. Okay, it's similar set of parameters, temperature and pressure, but you go down in mass to increase the length, okay? Then you can actually detect even things like gravitational waves. And these work in a different domain completely so it's low frequency. So they are complementary to LIGO. They're in the same regime as what LISA and others would do, but these are meter scale. Okay, so you can have many of them, you can have a network of them, and then you can probably get the complete tensor nature of the gravitational wave, its direction to the source. All those we have not calculated yet, but we have one basic publication on this detection under some simplifying assumptions. Oh, just before finishing, I would like to re-emphasize the point on the entanglement through gravity. I mean, there are various ways of stating what we conclude from that. Okay? One way of thinking about that is that you can see directly from the picture. What is in superposition is the point from which the virtual gravitons start and the point at which they end. Okay? So that is the kind of thing which is verified in our experiment. Okay? Also, so what would happen, you might ask, if gravity was not quantum? Okay, that answer depends very much on in what way one does that non-quantum. Okay, So if you are if for example, one thinks that when a mass is large enough, it collapses to one state or other. Okay, so then gravity will be fully sourced as being a centered here or centered there. Then you can see that only one of these four diagrams will be there. Okay, so so that then obviously there will be no entanglement, and so you can so when you do not get entanglement, generally you cannot conclude so much about a specific classical theory, but you can do the other way around. If you take various classical theories, you will see that they do not entangle, which is trivially true, because we showed that if you have a classical field source, so the entire thing just sources a classical field there, then it will just do a rotation there or a positive map on that, which will not entangle, right? So that's pretty much all. Okay, so I'm happy to open the to discuss a little bit. I think okay, so there was already some question, right? Yeah, so there was a question, right? And I now return to that question a little bit. What was that? So yeah, can the experiment be developed to experimentally observe the virtual graviton? So we are kind of saying that this is it. This experiment that I've described is it. Okay? It can be used to, see the virtual graviton, because this is the virtual graviton being exchanged. It evidences the quantum nature of the virtual graviton. Okay? Not more. When you observe, you always a detector click, so you do not see a virtual particle. Actually, you see only virtual particles through the indirect effects on other objects. Yeah, so that's kind of it. Yeah, so you can ask me more questions.
Yeah, there are more questions in the chat box. So if you can stop presenting, the questions are there. You can see.
Okay. Yeah. Stop share.
Yeah. Is all types of entanglements caused due to mediators? If so, does the entanglement entropy between the interior and exterior of a black hole horizon also caused by mediators which somehow escape the black hole horizon?
Is all types of entanglement caused due to mediators? If so, does the entanglement entropy between interior and exterior of a black hole horizon also caused by mediators? Okay, so a good question, but I wouldn't say that all types of entanglement are caused by mediators, okay, because you can have entanglement between two things which are local, okay. So you can have entanglement between a mass and it's the on-shell gravitational field modes around it, okay. So like you can have an interaction, an entanglement between an atom and a photon, okay, where the photon has locally interacted with the atom. So so you can entangle as soon as you have an interaction vertex, okay. However, you will not. You have to prepare your initial states carefully. Okay? So you have to prepare the initial states of the two things which are interacting with some delocalization in the operators through which they are interacting, so that they get entangled. Okay, if they are eigenstates of the operators which are interacting in the vertex, then you will not entangle. Okay? But generally, those are very special states, right? So typically, you will have things in states which are not in particular eigenstates of their interaction. So you will. So entanglement is very generic in quantum information theory, right? So it's hard not to entangle. Okay? You have to prepare special states, but if you want to, on the other hand, if you want to maximize entanglement as we wanted in our case, then you better optimize your thing. So if you prepare the most non-eigenstate of the operators which are interacting in your vertex, you will entangle. But that to generate those states, on the other hand, you would need virtual processes. Okay? So virtual process would be required at some level. So you like a tunneling generates superposition. So to prepare those initial states, you would need a virtual process probably to create a superposition. But otherwise, yeah, generically you do not. Yeah, if you had such states created by other virtual processes, then a single vertex can also entangle.
The next question I don't think is very relevant to your talk. Can such quantum computers be used to cure many diseases?
I can only be amused by that question, but people do look at other things, like people look at injecting nanocrystals and then going, but I don't work in that area. So
how much are we close to get a complete configuration of the quantum? Well, we already have some.
Yeah, there are some quantum computers. Again, my talk was not in that topic, but people have quantum computers of several qubits.
The next question is a long question. You can read it out.
If we are assuming that particles are locally interacting with the gravitational field, so can we say that this is an assumption of locality as in Bell's inequality, and then the particle has a definite predetermined mass on similar basis? If the field is interacting locally when the particle, then a predetermined property of the field. Sorry, okay. Maybe I just clarify one thing. So the assumption of locality in Bell inequality is a bit different from the. So what I highlighted as locality was the locality of physical interactions in any relativistic theory, okay, including quantum field theory, but in any relativistic theory, even classical relativistic theory, the interactions must be local. Just because things have to go at the speed of light, you cannot jump and interact at a distance. Okay, of course, in some theories, some fundamental theories, there could be some basic length scale over which interactions are smeared, but this could be a very small length scale. So like a string length scale or some other fundamental mass scale, which is so small that it's pretty much local over the distance of separation of our apparatus. Okay? So that is a locality arising due to protecting relativistic causality over the distances over which our interaction works. Okay? Bell locality is something else, that the choice of basis of one observer should not affect the outcome of another observer. Okay, that is different. That is again of course, from relativistic causality, but it is slightly different from. You do not have to assume any interaction. It is just a observation that this otherwise relativity will be violated, right? So if your choice of basis which you're making at free will on one part affected which outcome you get on the other side, right? So that is locality used in Bell's theorem. Okay. I don't know whether this suffices. You have some questions about the mass as well, but we are taking masses in kind of eigenstate. It's like a Fock state. Okay, so so it's a single mass value. So there's no no superposition of different mass states, for example, okay. Or different energy states for that matter. Okay. Well, there are superposition of different energy states in the totality of our configuration. Okay. So if you included the interaction energy, then those all four would be different mass states. So would a consistent theory involve a force mediated by a hypothetical graviton or be a product of discrete structure of space-time itself? Are there deviations from operational relativity at very small or very large scales, or in other extreme circumstances that flow from? Yeah, I mean, the thing is, what I've said, this experiment is quite agnostic to what is the ultraviolet theory of gravity, of quantum gravity. Okay? So what happens to gravity in very small scale is not a question I examine at all, because anyway, our distances are hundreds of microns. Okay? At such distances, it's very well known that you have Newtonian interactions, very well tested, albeit not yet tested for small masses. Okay, so if there's some mass dependence of that, we don't know. But any theory of quantum gravity should boil down to this theory of local perturbations being quantized pretty much like electromagnetic field is quantized, they come down to that, okay? So whether you consider loop quantum gravity or string theory, everything comes down to that thing, okay? Or I would even tell that any bona fide theory should come down to this to be a consistent quantum theory at this level, okay? Because this is a mechanism which explains the Newtonian interaction through in a quantum mechanical way, okay? So we cannot constrain theories or tell anything about theories at this level through our experiment. Yeah. There has been one paper by some other people on seeing the discreteness of time through our kind of setup. So you can read that up, but typically it's very hard to say anything about gravity and what is the true underlying theory of quantum gravity, we cannot say. Just we say it's a Bell-like test. We just say whether it's quantum or classical. Is there a difference between entanglement generated by a virtual graviton and yes? So this is a very good question. So the entanglement generated by a virtual graviton and entanglement by a real graviton. Okay, so this is a very good question. This is an important question. Okay, so when you say I could go back to that picture I had in the beginning of these qubits. Okay, because qubits have been entangled in both kinds of ways. Okay? You can entangle a qubit with E and being a photon of some polarization emitted, G a photon of opposite polarization being emitted. Okay? So that is an entanglement of a qubit with a real photon. Okay, and then that photon can go to the other qubit and exchange its entanglement. Okay, but you see what has happened during this. Okay, during this thing, this first qubit would have become gone to a fully mixed state as soon as this photon left, right? And so this qubit is in a mixed state, but that other qubit is not yet entangled with anything. So it's still in a pure state. Then after speed of light time, when this hits, then that photon starts being entangled with this, and then this decouples, okay? So then it is entangled with that, and both are in a mixed state, okay? So there will be a fall of purity of one qubit without yet entanglement developed with the other qubit, because actually it's entangled with some intermediary. Okay, so that's what happens when you have, real photons involved. Okay, of course, as I said, there are virtual processes involved in creating the initial E plus G, or E and one polarization, G and another polarization, but that's a different aspect. Okay, so that's the comment that you cannot do anything without virtual processes really at some stage. Okay, but once you have created a superposition which involved some sort of virtual process like a tunneling, then you could have real photons propagating and transferring the entanglement elsewhere. However, when you have entanglement mediated by virtual photons, the thing is that it's always a coherent interaction. When as much purity of this drops is as much purity as this drops in the ideal case. So it is really related to the entanglement building up. Okay, so the intermediaries, they do not get entangled with this system when they mediate the entanglement. Okay. This may look a bit surprising, but this is what comes out from the interaction. The maths gives you a coherent interaction. Okay. It will be like a coherent gate. Like really, you can write an interaction which involves only those two masses, and there's no gravity in the interaction itself. Okay. So we are bringing in the gravity by assuming relativity, that something has to go. And the nature of the interaction is dictated by, the strength is capital G, treated by gravity. So, but intermediate there is, so that's what happens when you have virtual graviton. So in this sense, maybe this is a good way to answer also the previous question. If your entanglement is continuously growing in time, as if it's generated by interaction Hamiltonian, then it's mediated by a virtual process. If your entanglement is not growing in time that way, it is 0, 0, 0, and then it starts suddenly grows after a while. Okay, so it depends on how much time you take to do here and how much time you take to there. Okay? Essentially the purity will fall. It's a tripartite system, okay, entanglement wise. Okay, you have something else in the middle time. Okay. Next question is, will closed time like curve arrive? Okay, so I should have, so our thing is valid. If you had closed time like curves and things, the arguments that I told will not be valid. Okay, so it's understanding that you are operating under in a fixed background, which is well, almost Minkowski, almost flat space, and also sufficiently smooth. I mean, you can do it near Earth, of course, so it doesn't have strange features. Okay, so then you can violate those LOCC and things like that. So you have to protect things like chronology. So the background has to be not pathological. Okay. How can mass exist in two states? Okay, the mass is not existing in, the mass is existing in two places. Okay, the left or the right. Okay, is created in a superposition. So the mass itself is we are not creating any superposition which has uncertainty in mass. Okay, it has uncertainty in the position of the mass. Okay. If you wanted to create uncertainty in the mass itself, that's much more difficult. Okay, and you would require well, any energy superposition will create is effectively a mass superposition, but it will require a lot more energy first of all, okay, depending on the level of mass change that you have to do. Here we are just displacing mass one way or other, but we are doing that in superposition. Next question is, you mentioned a coherent superposition. Okay. So what is a coherent superposition? So a coherent superposition is a superposition where the off-diagonal components, say you superpose 0 and 1, the density matrix has 0, 1 component, that is significant. Okay. So you can tell that you can do our experiment this way, that if you, if you assume Rovelli and others, they presented this, yeah, with so there you have a gravity centered here or gravity centered there, gravity centered there, gravity centered there. Then actually, if you explicitly spoil the coherence, then our effect will go away. So it is the off-diagonal coherence, including the gravitational field, is a necessity for our experiment. Can photons or any massless particles also be influenced by gravity? Yes, of course. Photons are influenced by gravity. In general relativity, photons bend. However, to make our experiment strong enough for a group of photons, we haven't been able to get a good scheme like that. Yeah, you will require. So what is there in our scheme essentially is a known state. Okay, so all atoms of the crystal fully going left or fully going right. This is what we call a known state. Okay, to create such states for photons, for very high number of photons, is very difficult. Okay, the effect is not that prominent if you have individual particles splitting. Okay, that's like how a Bose-Einstein condensate would split, like a BEC would split. Yeah, the effect is not based on the effect is based on all ingredients moving one way or other. Yeah, if the whole mass moving one way or other. Okay.
This is the last question, I think, for the day.
Okay. Gravity becomes strong force for particles only at blank scale. Why are the scales so different? This is not a question I'm familiar to. So you have to ask this question: why gravity becomes strong, like matches other forces in the Planck scale? You have to ask this to a particle physicist, really. Okay. This is I've not given the talk in that domain. Okay. But essentially, coupling constants run, and they all come together at different scale. Okay. You can look this up on the web somewhere. You will find answer to this question. Okay?
Chiranjeev, can I ask a quick question? Very quick. So Graviton has this spin, and the game you had really involves spin in a very involved. It's really is an important ingredient. So what happened to spin angular momentum conservation in this? So when you are saying graviton is absorbed, I believe you want to absorb the spin in a coherent way so that everything remains coherent. If the graviton spin is not being absorbed properly, then I think you will have decoherence. So now, but in the argument, somehow I did not see the presence of graviton's spin. So where did it go in the wave function? And
no, I think it is. The spin degree of freedom is still there. So
is it summed over? Is your argument summed over all possible?
Yeah. It is indeed. It is summed over, it was there in that slide, which was how the gravitational interaction, arises. Yeah. So you see, it is in those indices.
Indices, I see.
Okay.
So your effect is such that this index is summed over and it survives it.
Yeah.
If there is a randomness in this index, then it will decoher. Is that correct?
Yeah.
And is there a mechanism by which it can happen? Sorry, is there a mechanism by which it can happen?
Not really, because these are being both sourced and absorbed by masses here. You see, it's kind of an internal mechanism. If you put a third mass here, then they will also exchange virtual gravitons with that one. Okay. And that will cause some randomnesses in the masses.
Exactly. That's my concern. Yes.
Yeah. So other presence of other masses do decohere.
I see. So this is the mechanism by which it can decohere, because there is no mechanism by which you can shield the graviton, and that's probably a trouble for this experiment, right? Am I
not necessarily trouble? We think of it as an advantage that electromagnetism you can shield, but you're right. You cannot shield other masses.
Yes,
right?
the
so it's both advantage and trouble. So it is advantage for those two masses because you just put a Faraday box.
Okay? Yes.
But it is disadvantage for the third masses, but which is also solution is given by Einstein, right? There, so we, in an idealistic world, we put it in this freely falling box. So we.
Does that mean it polarize? It's kind of. Does it polarize the graviton in some sense? Are you saying?
No. It just gets rid of the acceleration. So it doesn't get rid of the curvature due to the other masses.
And torsion. If you have torsion field, will it lead to decoherence because of rotation of this graviton?
That's a very good question. Yeah, torsion. We have not analyzed torsion in this setting, though my collaborator Anupam sometimes brings that up. Yeah. So what will happen with fields with torsion is an interesting point to see.
I see. Okay.
We have not analyzed that.
Thanks a lot. Thank you.
Okay, so thanks a lot for giving such a wonderful talk and interactions. So both Prashant and I would like to thank you for giving the talk and giving your time. Okay, we'll hope to see you in a more regular way.
We should catch up sometime.
Sogat, I wanted to tell you that the Subhayan Roy Maulik with whom I did this closed timeline curve.
Okay.
You have cited that. See, we used to play around, but then this guy went to Oxford. He did his PhD. Now he has gone to Berkeley.
Has he? Okay. What field is he working on?
Quantum computation more towards computer.
Okay.
Because he's a computer science background guy.
I see. That is good to know. Yeah. What was his name again? Can you tell me?
Subhayan Roy Maulik. You have cited that paper.
Okay. Definitely. Thanks very much for your attention. Okay. Bye.
Karthik, are you around?
Yeah, yes, sir.
Yeah, you can load your...
Okay, I will start my presentation. Okay. So, am I audible clearly, sir?
Yeah, you are audible clearly. Let me formally introduce Karthik Selvan. Karthik, I would say, is a true researcher in the sense that, he is always busy with research. He's an original thinker and a physics teacher. Now, you'll be amazed to know that, he's trying to get into PhD program because of a variety of reasons. For example, now it is COVID, earlier it was a job where he was in. But it has not stopped him from producing very high quality work, including, a single author paper. And I would say that, he was visiting us for some time, and very remarkable piece of work I could do with him. And, he has, this EIT, electromagnetic induced transparency, those things I really understood from his, discussions, and, went on to write a paper on that. So, Karthik, you are now, requested to give a talk.
Yeah, okay, thank you. Okay. So is my screen visible, sir?
Yeah, it is visible.
Yeah, it is visible. Yeah.
Okay. So thank you, sir. So good evening to all. So first of all, I would like to thank Professor Prashanta K. Bonigrehi and other organizers for giving me this opportunity. So this is going to be very basic talk. So I'm a little bit uncomfortable to give talk after Professor Sagoto Bose. Okay, so the most of the topic concepts I'm going to discuss may be familiar to many of the audiences. So the topic I'm going to discuss is entanglement detection conditions. As we all know, entanglement is used as a physical resource for quantum teleportation, superdense coding, and other quantum information processes. So we must be able to detect and quantify entanglement. In this talk, I'm going to discuss about detection of entanglement. I won't discuss about quantification of entanglement. So the objective of this talk is to discuss about the separability conditions for 2-qubit systems, 2-mode Gaussian states, 2-mode non-Gaussian states, and multi-mode non-Gaussian states. Mainly, I'm going to discuss two methods. So one is the positivity of partial transposition, and another one is finding lower bounds for sum of variances in the case of separable states. So for the first three systems, 2-qubit systems, 2-mode Gaussian states, and 2-mode non-Gaussian states, I'm going to describe the results published by other researchers. And in the last system, multi-mode non-Gaussian states, I'm going to consider one particular state, and I'm going to describe the entanglement condition for that type of state proposed by myself and Professor Prashanta K. Bonigrehi. Okay. So first I will describe about 2-qubit systems. So the state of a 2-qubit system is represented by this ket vector, and in this ket vector, I and j's, it takes values of zeros and ones, and the Cij is for probability amplitudes, and the corresponding density operator is given here. It's outer product of the state vector. But in general, we use a density operator to describe a mixed state. So mixed state is a statistical mixture of pure states. So in the expression of mixed state given here, this Pj is the probability of finding the system in the pure state rho j, and these probabilities they add to 1. Okay, so now the properties of density operator. So the density operator is a Hermitian operator, and it is a positive operator. So specifically, it's a positive semi-definite, meaning the eigenvalues are non-negative, and the trace of rho is equal to 1, and the trace of rho squared is equal to 1 for pure state, and it's less than 1 for mixed state. And for any observable A, the expectation value of the observable is written as a trace of A times the density operator, and the variance of this observable is given here, and this variance is a non-negative value. And for any operator B, it may not be a Hermitian operator. The expectation value of B dagger and B is also non-negative, and this is a consequence of positivity of the density operator. Okay. So now I'm going to describe the entangled state of a 2-qubit system. So the state of a 2-qubit system is entangled if it is not separable. That is, if the density operator of the state or the system cannot be written in this following form, then that state is the entangled state. Otherwise, the state is separable. So in this expression, we have a statistical mixture of product states. So rho 1 is the density operator of the system 1, and the rho 2 is the density operator of the system 2, and all the realizations are in the product state. So now the question is how to detect the separability of bipartite states, and the answer is using partial transposition. So first, the transposition is a positive map. So positive map means we call a map as a positive map when it transforms a positive operator into another positive operator. Here the density operator is a positive operator, and this transposition, it takes a density operator into another valid density operator. However, the partial transposition, it is a positive map only if the state is a separable state. Okay, if the state is not separable, if it is entangled, then this partial transposition is not a positive map. So we are going to make use of this property of partial transposition to detect the separability of 2-qubit systems. Okay, so here I have shown an example. I have considered a Werner state. This phi is one of the Bell state, and this P, it takes values between 0 and 1. The density of matrix of this state is given here, and one can verify that the eigenvalues of this density matrix is non-negative for all values of the P. However, if we do the transpose of the first system, we end up with this matrix, and this is the partially transposed density matrix. And for this matrix, one can find that one of the eigenvalue is negative for the values of P in the range between 1/3 and 1. So this implies that for this range of values of P, the state is entangled. And for the values of P in the range between 0 and 1/3, all the eigenvalues are non-negative. And for this range of values of P, we can write the density operator as a convex combination of product states. So the positivity of partial transposition, in short PPT, is a better condition to detect the separability than other inequality relations such as Bell inequality relations. And this PPT is a necessary condition for separability of a bipartite system. So the necessary condition means if the state is a separable state, then it has to satisfy this PPT condition. And it was shown later that this PPT is both a necessary and sufficient condition for separability of all 2x2 and 2x3 systems. So the sufficient condition means if this condition is satisfied, then the state is separable. Okay, so this is for a 2-qubit system. So now I enter into the continuous variable systems. So specifically, I'm going to consider 2 modes of electromagnetic field. So this is the Hilbert space of 2 modes of electromagnetic field. This is tensor product of H1 and H2. And H1 is the infinite dimensional Hilbert space of mode 1, and H2 is the infinite dimensional Hilbert space of mode 2. And this is the Hamiltonian of the system. Here, Q1, P1, Q2, and P2. These are dimensionless quadrature operators, and these quadrature operators are related to the creation and annihilation operators as given here. And all these 4 sets of operators, they satisfy these commutation relations. Okay. So now I combine the quadrature operators into a vector as given here. Then in terms of this vector components, I can write the commutation relation given in this last line in a compact form as given here. Here omega KL is the element of the matrix omega, and this matrix omega is called symplectic form, and for 2 mode system it is given here. And the elements of covariance matrix of this quadrature operators are given here. So from this commutation relation and the elements of covariance matrix, we can find that the sum of VKL plus I/2 times omega KL is equal to expectation value of the product of RK and RL minus the product of expectation values of RK and RL. And the covariance matrix V is a symmetric matrix, and it is also positive semi-definite. And this symplectic form omega is anti-symmetric, and hence this I times omega is Hermitian. And one can verify that this V plus I by 2 times omega is a Hermitian, and it is also positive semi-definite, meaning the eigenvalues of this matrix is non-negative. And this matrix in equation, it describes the uncertainty relations between quadrature components. Okay, so in the 2-qubit systems, actually what we did is we directly found the partial transposition of density operator, but in the continuous variable systems, we are not going to do that. We will consider how the covariance matrix V is transformed under partial transposition. So for that, we have to know how these operators, creation and annihilation operator and the quadrature operators, are transformed under partial or under transposition. So for that, I have written the creation and annihilation operator in matrix form in fog basis. So we can verify that the partial transpose of this matrix is equal to this matrix, and similarly, the transpose of this matrix is equal to this matrix. So from this, we can say that under transposition, the annihilation operator is transformed into creation, and the creation operator is transformed into annihilation. And these quadrature operators, they are related with creation and annihilation operator. So from that relation, we can find that the Q operator remains unchanged, whereas the P operator, it undergoes a sign change. So in the calculation, what will we do is, if you want to find the effect of a partial transposition, so in the covariance matrix, all we have is expectation values. So before taking expectation value, these RK and RL can be expressed in terms of mode creation and annihilation operator. So before taking expectation value, we will replace A by A dagger and A dagger by A, and then we take expectation values. Okay. So in the system of a two-mode Gaussian state, the partial transposition of second mode, it can be represented by the matrix given here. So it's a diagonal matrix. The last element is -1, and the other 3 diagonal elements are 1. So under partial transposition, the vector, the components are the eigenvalues of the quadrature operators. It is transformed into this, and here the first 3 elements remains unchanged, and the sign of the last element is changed. And under this partial transposition, the covariance matrix V is transformed into V prime, and its expression is given here. So now if the state is a separable state, then this covariance matrix V prime must be positive, and it has to satisfy this condition. That is, V prime plus I by 2 times omega must be greater than or equal to 0. That is, it has to be a positive semi-definite matrix if the state is a separable state. If the state is entangled, then under the partial transposition, this V prime, the covariance matrix, it won't be a valid covariance matrix. And say the Gaussian states, they are described completely by the covariance matrix. So that's why we use the covariance matrix here. And this condition is a necessary condition for separability. And it was shown by Professor Simon that this condition is also both a necessary and sufficient condition for all two-mode Gaussian states. Okay. So now I'm going to describe another method. So this method was proposed by Duan et al. And so they considered a pair of operators. These operators were written in terms of the quadrature operators. And what they did is they showed that there exists a lower bound for the sum of variances in the case of separable states. Okay, so we have a variance of operator U and the variance of operator V. And for this sum, there exists a lower bound for separable state. And this result is obtained using Cauchy-Schwarz inequality relation, and the fact that the expectation value of product of operators can be factorized for separable state. And it is a necessary condition for separability, and they also showed that it is a necessary and sufficient condition for two-mode Gaussian states. So in the Gaussian states, we have considered only the variance matrix, which involves only second moments. But for non-Gaussian states, these conditions, using this condition, we can't detect the separable states or the entangled states. So it was pointed out by Professor G.S. Agarwal and Professor Biswas that one has to use a higher order moments in order to detect the separability of non-Gaussian states. So in their work, they considered the operators K1, K2, K3 as given here. And these three operators, they satisfy SU11 algebra, and this algebra is given here. And what they did is they considered the Heisenberg uncertainty relation of partially transposed K1 and K2. And that Heisenberg uncertainty relation is given here. And this condition is valid if the state is separable state. So if this condition is violated, then the state is entangled. And later, it was shown by Professor Na and Kim that this condition, it can be written in this form. Here the operators J1 and J2 are given here. And these two operators J1 and J2 along with the operator J3 are given here. They form SU2 algebra. And there is another condition based on some uncertainty relation. This condition was proposed by Professor Hillary and Dewberry. So they considered these operators J1, J2, and J3, and they calculated the variance of operators J1 and J2, and they showed that there is a lower bound for separable states. And they arrived at this result using the fact that the expectation value of product of operators AB can be factorized for separable state, and this Schwarz inequality relation. And so this is a condition for separability, and this condition is violated if the condition given here is satisfied. So one can use this condition to detect the entanglement of two-mode non-Gaussian states. Now the question is how to verify the violation of the separability condition. So for that, one has to measure the operator J1 and J2 and the NA plus NB, and this can be done by using a beam splitter. So it is shown here. So we have a beam splitter here, and mode A is injected in one input mode, and mode B is injected in another input mode. But the mode B is a phase shifted, and the C and D are the output modes, and they are given here. And in the output, what we do is we detect the photon number difference and the sum of photon numbers. See, the photon number difference, it gives the operator J1 when the phase shift is equal to 0, and it gives the operator J2 when the phase shift is pi by 2. And the sum of photon numbers, it gives always NA plus NB. So using this experimental setup, we can verify the violation of this separability condition. Okay. So now I enter into multimode non-Gaussian states. So I consider a specific state, the W state. So 3-mode single photon W state, it is given here. So for this state, the probability amplitude is same for all Ket vectors. And this state is not biseparable, and it retains a pairwise entanglement. Now, how to detect the entanglement of the state? So far, we have considered only 2-mode systems, but now we have a 3-mode system. So how to detect the entanglement of this state? So one can detect the entanglement of this state by detecting the pairwise entanglement using the 2-mode entanglement conditions described before. So what we have to do is we have to detect the entanglement between the modes A and B using this condition, and then entanglement between modes B and C using this condition, and similarly for mode C and A. So for n modes W state, one has to use n into n minus 1 divided by 2 inequality relations. So now the question is, do we really have to verify these n into n minus 1 divided by 2 inequality relations? The answer is no. We no need to verify all these inequality relations. So in the multipartite system, a multipartite state is genuinely entangled if it is not biseparable. And it was shown by Hillary and Dewberry that a 3-mode system is genuinely entangled if its density matrix cannot be written as any of the forms given below. So in the first form, A is separable and B and C are considered together. And in the second form, C is separable and A and B are considered together. And in the third form, B is separable and A and C are considered together. If the density matrix of our system cannot be written in any of these 3 forms, then the density matrix represents a genuinely entangled state. So now how to verify that? So for that, we have to use only 2 two-mode entanglement conditions. What we have to do is first we have to detect the entanglement between mode C and A. So if the mode C and A are entangled, then the density matrix cannot be written in this form, the first form, and similarly it cannot be written as given in the second form. And similarly, if the modes C and B are entangled, then it cannot be written as given in the third form. Okay, so if mode C and B and mode C and A are entangled, then the state is genuinely entangled. So for three-mode system, we have to detect only two inequality relations. So we can extend this argument, and for n-mode system, one has to verify the entanglement of one mode with the remaining n-1 mode separately. Okay, so for n-mode system, we have to perform this experiment n-1 number of times. So here I have shown it for a three-mode system. So in the three-mode system, what we have to do is first we have to detect the entanglement between mode C and A, and then we have to detect the entanglement between mode C and B. So here we are doing the experiments 2 times. So what if instead of sending this modes A and B separately, if we send the superposition of A and B? So this is the question we considered. So instead of A and B separately, what if we send the superposition of A and B? So if we analyze this, we will end up with a multimode entanglement condition, which is a sufficient condition for entanglement and a necessary condition for W state. So for this input mode, so in one input we have a superposition of A and B, in then another input we have a mode C, and if we detect the photon number difference at the output, we will get these operators L1 and L2. So that is what we have described in our research paper. So the entanglement condition for W-type states. So by W-type states, I mean the states which are not biseparable and they retain pairwise entanglement. So W state is one such state, and the whole states belonging to W class satisfy this definition. And in addition, we have in quantum optics the other states which will also satisfy this condition. So we consider the operators L1, L2, and L3, and these three operators satisfy SU2 algebra, and we derive the sum of the uncertainties of L1 and L2, and we found a lower bound for separable states. So this is a separability condition. So to get this result, we used the facts shown here. So yeah, these facts. So for a separable state, the expectation value of product of operators can be factorized, and this sorts inequality. So, yeah. So here the separability condition means the state is fully separable. Okay, so since we are now considering multimode system, we can have even biseparable state. But this condition, it is a condition for fully separable state, and this condition is violated when the condition given here is satisfied. So one can use this condition to detect the entanglement of a multimode system, and this condition is a sufficient condition for multimode entanglement, and it is a necessary condition for W-type states. So if we have a W-type state, then it will certainly satisfy this condition. So next we considered the uncertainty relations of partially transposed SU11 algebra operators. So we consider these three operators K1, K2, and K3, and they satisfy SU11 algebra. And this is the Heisenberg uncertainty relation of partially transposed K1 and K2. Here we transposed only the third mode C, and this inequality relation is satisfied by separable state. And if this condition is violated, this equation is violated, then the state is entangled. And this equation can be written in terms of SU2 algebra operators as given here. And in addition, we considered Schrodinger-Robertson uncertainty relation, and the Schrodinger-Robertson uncertainty relation for partially transposed operators K1 and K2 can be written as given here, and it can be expressed in terms of SU2 algebra operators as shown here. So if we compare this equation and this equation, see the lower bound is larger when we use the Schrodinger-Robertson uncertainty relation, and hence this provides a more strict condition. And if this entanglement condition is satisfied, it guarantees the violation of these two equations that we have shown in the paper. And these results, they can be extended to n-mode system that I didn't show it in the slide. Okay, so now the question is how to produce the superposition of n-1 modes. So this diagram I showed that instead of sending A and B separately, we can send the superposition A plus B divided by root 2. So for n-mode system, we will have a superposition of n-1 modes. So how to produce that superposition? So we can use multi-put beam splitters or a linear array of beam splitters with different splitting ratios. In the case of a frequency mode, we can use multi-lambda IIT systems. So using multi-put beam splitters and the multi-lambda IIT systems, we have shown the experimental scheme in the paper. So the conditions for non-Gaussian states I described in this paper have certain limitations. We can have a mixed states. The states which is a convex combination of this biseparable state and this biseparable state and this biseparable states. So if you look at each of these realizations are different. So in the one realization, A is separable and B and C are entangled. And in the another realization, B is separable and A and C are entangled. The third realization, C is separable, A and B are entangled. We can have such mixed states. So by definition, these mixed states are not genuinely entangled. But using the two-mode entanglement conditions and discussing this talk and our multi-mode entanglement condition, we can't distinguish this type of mixed states from the genuinely entangled states. So for these states, one has to use the entanglement fitness operators in order to distinguish them from genuinely entangled states. And there are certain asymmetric states belonging to W class which will not satisfy the multi-mode entanglement condition for certain permutations of mode operators. So in our condition, see this diagram. Here we have a superposition of A and B and the mode C here. Instead of this, we can have mode B here and A and C here, or mode A here and B and C here. So we can have any combination. So these results have to be changed accordingly. And certain asymmetric states belonging to W class, they won't satisfy this condition for certain permutation of mode indices or mode operators. So we have addressed this issue in our current research work, and we have given a solution to this problem. Okay, so these are the references. So I have described results from 10 research papers. And thank you.
If anyone has any question, he or she can unmute and ask the question.
I think this is a very basic talk. No one will have questions.
No. See, there are questions. There are questions.
Okay.
People are a bit sad, but people are a bit sad. See, for example, the kind of things which you have done based on which, I mean, I am also there, SU2, SU11 kind of things, right?
Yes.
So, is it possible to connect them with steering, just like Robertson Schrödinger uncertainty they got connected with steering? This Schrödinger's steering.
Okay, so just steering, you're saying?
Steering inequality. Remember that entanglement is one, but Schrödinger had pointed out that steering basically you can steer somebody.
Okay, yes.
Do you have any thought about that? Steering?
No, sir, I didn't think about that. Okay.
And what is the experimental thing? Like in IBM, somebody has looked at our kind of thing.
I think long back, because he sent some paper, I think he has verified this condition.
Meher. Vikas and Meher did something, but
yes, sir.
Right. But the type of operator which we did for this Journal of Modern Optics, that I don't think has been verified.
This kind of operators,
the kind of witness you came up, it was essentially your idea that with that kind of witness, can we think about in some kind of IBM kind of configuration?
Yeah, actually, yes, I think we can.
The main point what I'm saying is that Bell state, GHS state, all these things are prone to disturbance, decoherence, those kind of things. Yeah. Now the question is how far we can go in this noisy, this ESQ atmosphere, to check our kind of witness. That's what I'm asking.
On IBM computers, I think it is difficult to realize the bosonic system.
Yeah, that is true. That is true.
But for two modes, we use a beam splitter. I think beam splitters, they are realized on IBM quantum computers. I've seen some papers. But now here we have more than two modes. So the operation is a bit complicated. I think more than two beam splitters, I don't know how to do it on.
See, Professor Vedral, if you remember, and you can go to his talk later, Professor Vedral, he pointed out that this field theoretical way of printing is much more advantageous as compared to writing them as matrices. It brings out, the local, non-local natures very nicely. So maybe one can think about some of those kind of things. Okay, if there are any questions in the chat box?
There are no questions in the chat box.
Okay. So if not, let us thank Karthik. Karthik, thanks a lot.
Thank you, sir. Thank you very much.